Hi everyone. In the last few classes, we have discussed about properties of self-adjoint, normal, and point positive operators. Today we are going to discuss about spectral theory of operators. Instead of looking at spectral theory of operators, we discuss spectral theory for an element in a Banach algebra. So we start with Banach algebras. So we have already discussed about Banach algebras earlier. So we say A plus dot with circle with three operations is an algebra if A plus dot is a vector space over the field F. So in our case we consider only complex field, and A plus with circle is a ring, and the third condition is alpha A circle B is alpha A circle B, that is A circle alpha B for every A B in A, alpha in the field F. So notation, for notational convenience, so we write AB in place of A circle B. So if you have an algebra, if there exists a norm satisfying norm of AB less than or equal to norm A and norm B, such a norm we call as algebra norm. So if A is an algebra and this is a norm on AB on A such that norm of AB less than norm A, norm B for every A, B in A, then A with this norm is called a normed algebra. So this norm is known as algebra norm. So a complete normed algebra is known as a Banach algebra. So Banach algebra means, so a complete normed algebra. This we have already discussed and we have seen few examples also. Now we are interested in looking at the spectrum of an element in a Banach algebra. So let us quickly recall when X is a Banach space, and Bx set of all bounded linear operators, set of all T from X to X, T is linear and bounded. So we know that Bx is a Banach space with the operator norm is a Banach space. So norm of T we write as supremum of norm Tx, where X is coming from X with norm X equal to 1. So this is called the operator norm of T, and we know that Bx is a vector space if you take S and T in B of X, St in B of X. So we define S plus T at X is Sx plus Tx, alpha T at X is alpha times Tx for all x in X and for all alpha in C. then we can say that this is a vector space, and the product of two operators is defined as is a composition S of Tx for every x in X. So with respect to all these operations, Bx is a Banach algebra. So first example, and we have seen some other examples also. So we have taken A as C of K. K is compact Hausdorff space. And we know that when we take Fg from A, then define F plus G at T as Ft plus Gt, alpha F at T, alpha times F of T for every T in K and for every alpha in C. So we can show that this is a vector space, and if you define Fg at T as F of T into G of T for every T in K, and norm of F as this is supremum norm of mod F of T. With respect to these operations, we can say that C of K is a Banach algebra, and it is a unital, it has a unit. So the constant function, so 1 at T is 1 for all T in K. This is the unit element. Okay, and in fact we can show that any commutative unital Banach algebra is a subalgebra of C of K. So that we will be looking at a later stage. So these are the two important Banach algebras. Now our interest is in looking at invertible elements. So let A be a Banach algebra. So with unit which we denote by 1. So that means, so A into 1 is all the time A for every A in A. So we say A is invertible if A in A, let us take, let A be an element of A, then A is said to be invertible in A if there exists some B in A such that AB equal to BA equal to 1. In fact, you can easily check that such a B is unique. Such a B means existing B with AB equal to BA equal to 1. You can show that it is unique. It is called the inverse of A. So it is called the inverse of A and denoted by A inverse. Okay. Now we can ask the question, if you look at the Banach algebra of complex plane. So let us look at example. If I take A to be C, this is a vector space with usual operations, and norm, we define norm of Z as mod Z for all Z in A. So this is a Banach algebra. Now we know that every non-zero element here is invertible. So if A is in A not equal to 0, then A is invertible. That means that is C minus 0 Set of all invertible elements if you collect, that is C minus 0, and we know that this is an open set because its complement of the closed set 0 is open. So in fact we can say that this is open in C. Okay. So before generalizing this result to a Banach algebra in the general setting, let us make one comment that we can always assume that all the algebras are unital with unit 1, and we also assume that norm of the unit is 1. So these are the assumptions we make. So we assume that all the Banach algebras are unital. The second one is norm of the unit element is 1. Okay, so there is a reason for this. We can actually, if A is a non-unital Banach algebra, we can embed in that algebra in a bigger algebra which is unital. So for that reason we can say that we can always assume that the algebra to be unital. Okay, so that process we call as a unitization. I will just give a idea of unitization process. So let us take A to be a Banach algebra. So define A as A1 as A cross C. Now we want to make this as a Banach algebra. So let us take A lambda and B mu from A. Define A lambda plus B mu as A plus B lambda plus mu, and alpha times A lambda, we define this as alpha A alpha lambda and A lambda multiplied by B mu, we can define this as AB plus A mu plus lambda B, and this is lambda mu, and norm of A lambda, this is norm of A plus mod lambda. Now with these operations we can check that this is a algebra, and in fact we can show that it's a normed algebra which is also complete. That means it's a Banach algebra because A is a Banach algebra. Now in this case, this 0 1, if you take, that is an element of A. So claim is that 0 1 is a unit in A1. So let us take A lambda in A1, then look at A lambda multiplied by 0 1, see nothing but A and lambda. If you apply the definition you will get this. So therefore we can say that, so 0 1 is the unit element in A1, and we can also show that norm of this element is 1 by the definition. Now we want to embed A, so define a map, let us say eta from A into A1 by A is mapped to A comma 0 in A1, and you can easily check that eta is linear. and if we look at norm of eta A, is norm of A comma 0 with respect to the algebra A1. This is norm of A plus 0 modulus of 0, that is norm of A. So therefore eta is an isometry. Now eta of A is contained in A1, and from A to eta A there is a isometry and onto. So we can identify A with eta A, which is a subalgebra A1. We can in fact show that dimension of A1 quotient eta A as a vector space is exactly 1. Okay. So in this way we can actually embed a non-unital Banach algebra in a unital Banach algebra as an isometric embedding. So for this reason we always assume that all the algebras, all Banach algebras and sister algebras that we are going to consider are unital. Okay, so now let us look at invertible elements in a Banach algebra. So let A be a unital Banach algebra with unit 1. Sometime we write 1 suffix A, sometime we will not write. So we define GA as set of all A in A such that A is invertible in A. That means there exists a B such that AB equal to BA equal to 1 for this A. Now we can easily check that the 1 is always inside GA, but 0 cannot be inside GA. So GA is a non-empty set. Now the question we can ask is that what kind of nature GA can have? We can easily show that GA is a multiplicative group. So show that GA is a multiplicative group. That means whenever A and B are in GA, then show that AB is in GA. Okay. Now what can we say about this set GA? So let us go back to the complex plane. So if you look at set of all invertible elements, that is C minus 0, we know that it's an open set. Now we can ask the question, is it true that GA is open in A? We can generalize, can we generalize that result? So the question is the following, is GA open in the algebra A? So we are going to prove this result in an affirmative way. So before doing that, let us prove some important results related to invertible elements. Okay. So let us prove the following result. Let A be a unital Banach algebra with unit 1. If we take A in A with norm A strictly less than 1, then we can show that 1 minus A is invertible. So 1 minus A is in G of A, and not only that, we can actually write down 1 minus A as inverse of 1 minus A as summation n equal to 0 to infinity e power n. Furthermore, we can give an estimate for norm of 1 minus A inverse. We can say that 1 minus A inverse norm of this less than 1 by 1 minus norm A. So we are saying that whenever norm A is strictly less than 1, this 1 minus A is invertible, and the inverse is given by this series, and this series is known as Neumann series. So okay, so this is exactly a generalization of the result which we come across in complex analysis. We know that, let us quickly recall, if Z is a complex number such that mod Z is strictly less than 1, then we know that 1 minus Z is invertible, and 1 minus Z whole inverse is given by summation n equal to 0 to infinity Z power n, or summation n equal to 0 to infinity Z power n is nothing but 1 by 1 minus Z. This is a geometric series. Now the same result we are trying to generalize to an element in a Banach algebra. Okay, so let us try to imitate the proof of the complex version of this result. So let us, okay, now to show the series is convergent, so let us call this equation as star. To show the series in star is convergent, we have to look at the nth partial sum sequence of that. So let us define, let us write Sn as summation k equal to 0 to n a power k. This is 1 plus a square, so on, a power n. So if you look at a into s power n, that is nothing but a plus a square plus a cube plus so on a n plus a power n plus 1. So that means if you look at 1 minus a into Sn, that is Sn minus Asn, so we will get 1 minus a power n plus 1. Okay, now we want to show that Sn is convergent. So to show that, we show that it is absolutely convergent. So we have norm Sn, this is less than or equal to summation k equal to 0 to n norm of a power k, and we know that that is less than or equal to summation k equal to 0 to n norm a whole power k. So we don't need this. So we can actually say that if I take Tn as summation k equal to 0 to n norm a power k, this is less than summation k equal to 0 to n norm a power k. The right hand side series is convergent because norm a is strictly less than 1. So it is nth partial sum sequence of a convergent series, that is the geometric series. Now we can say that by the comparison test, so Tn is convergent. That is convergent. Hence the original series is absolutely convergent. Therefore but we are in a Banach space. We started with a Banach algebra, then we know that in every Banach algebra convergent series is convergent. So therefore we can say that summation is convergent. say the limit is, so this is b. Assume that this limit is b. Now we want to show that b is exactly inverse of a. So let us consider, so we want to show that 1 minus a into b is 1 and b into 1 minus a is 1. So 1 minus a into b, so b is nothing but limit of Sn, 1 minus a into Sn, but we know that 1 minus a into Sn is 1 minus limit n tends to infinity, this is 1 minus a power n plus 1. Now because norm a is strictly less than 1, a power n plus 1 converges to 0 as n going to infinity. So this is 1. So similarly, so check that b into 1 minus a, so this is 1. So we can say that b is nothing but inverse of a. Therefore, so b is 1 minus a inverse, but that is nothing but summation n equal to 0 to infinity a power n. Okay. So this is a proof of this result, and let us try to look at the bound for norm of 1 minus a inverse. So norm of 1 minus a inverse, so we have norm of b is limit norm Sn n going to infinity, but this is less than or equal to limit. So we have already computed what is norm Sn. Norm Sn is less than or equal to summation k equal to 0 to n norm a power k. So this is nothing but limit n tends to infinity so we can directly write this is exactly equal to 1 by 1 minus norm a, but b is nothing but norm of 1 minus a whole inverse. So this gives the bound for norm of 1 minus a inverse. Okay. So as an immediate corollary we can write the following. Let us take lambda to be a complex number such that norm a is strictly less than mod lambda. Then we can say that a minus lambda, or we can say lambda minus lambda into 1 minus a is invertible, and lambda 1 minus a whole inverse can be written as summation n equal to 0 to infinity a power n by lambda n plus 1. And moreover, norm of lambda into 1 minus a whole inverse is less than or equal to 1 by mod lambda minus norm of a. We can actually, so the proof is trivial, it comes from the earlier result, Neumann series. So we know that, let us write b as a by lambda. Lambda cannot be 0 because mod lambda is strictly bigger than norm a. Then norm b is strictly less than 1, and now apply the earlier result. to get the conclusion. So this is an easy consequence of the earlier result, which we call as a Neumann series. Okay. Now we want to discuss about what kind of nature the set of all invertible elements has. So we can show that proposition. The set GA is an open set. GA is an open subset of okay. So let us try to prove this one. So we want to show that every point is an interior point. Let us take A in G of A. Now let us try to look at this result in the complex plane. So we have shown that the set of all non-zero complex numbers are open. So if you look at here, so this is removed. If I take any complex number which is non-zero, now look at the ball centered at Z with radius Z. So the ball centered at Z with radius Z is contained in C minus 0. So that means this is an open set. We can get a ball around Z with some radius R which is contained in C minus 0. Hence we can say that. Now we can imitate the same thing, but here instead of Z we can write mod Z, we can write as 1 by mod Z inverse, then get the result. So the idea is this. So look, we have to look at the ball centered at A. So look at ball centered at A with radius 1 by norm A inverse. So we claim that ball centered at A with radius 1 by norm A inverse is properly contained in G of A. That means if you take an element B from this ball, we should be able to show that that is also invertible elements in A. So let us take B from ball centered at A with radius 1 by norm A inverse. Then we get norm of B minus A is less than 1 by norm A inverse. So if we consider norm of A inverse into B minus A, this is norm of A inverse B minus 1. So we can write the other way. So norm of A inverse A minus B. So this is norm of A inverse multiplied by norm A minus B. Because of the algebra norm, this is strictly norm A minus B is strictly less than 1 by norm A inverse. This is, so this implies 1 minus A inverse B is strictly less than 1. So this implies 1 minus A inverse B is in GA, or we can say that A inverse B is in GA. So we know that A is in GA because A is invertible. Now we also have concluded that A inverse B is in GA, but we know that GA is a multiplicative group. So using that we can show that. So we can say that B can be written as A into A inverse B, that is in GA. So this completes the proof that every point of this ball is an invertible element. Okay, so that means we can conclude that GA is an open subset of A. Now using this property we can also show that one more important observation about this GA. The map A going to A inverse is continuous on GA. A going to A inverse is continuous on G of A. Let us try to look at the proof of this one. So we want to show that if A is a sequence of element in GA converging to A in GA, we have to show that A inverse, AN inverse also converges to A inverse. So proof: let AN be a sequence of element in GA such that AN converges to A in GA. Okay, so now we want to show that AN inverse minus A inverse also converges to. So to show so for this purpose we use the following formula. So let us take so if you take two elements AB in GA, then we have B inverse minus A inverse. We can write in terms of A minus B. So this we can write as B minus A this is B inverse A inverse. So this is B inverse A minus B A inverse. So B inverse minus A inverse. Okay. So this is a very useful formula we will be using again and again. Now we want to estimate what is the norm of AN inverse minus A inverse. So let us call this as star. By star we can say that norm of A inverse minus A inverse, this is norm of AN inverse minus A minus AN into A inverse. So by the algebra norm condition we can say that this is norm of AN inverse norm A minus AN into norm A inverse. We know that AN converges to A, so on the right hand side norm of A minus AN goes to 0. Norm A inverse is a constant, and we don't know anything about this term, it varies with n. So if we are able to show that this term is uniformly bounded by a constant, we can conclude that AN inverse converges to A inverse. So to show for all n where k is positive constant. So this is what we want to show. So let us see. Now AN converges to A implies there exists a natural number n0 such that norm A minus AN is less than 1 by 2 times norm A inverse for all n bigger than or equal to n0. So let us call as this is inequality 1. Okay. Now if you look at A inverse into A minus AN, A inverse into A minus AN, this norm is nothing but 1 minus A inverse AN. So by inequality 1 this is less than 1 by 2 by inequality 1. So this implies 1 minus A inverse an is strictly less than 1 for all n bigger than or equal to n naught. So we can say that by the earlier result that we have proved 1 minus A inverse an is invertible. So we can say that A inverse an is in GA for all n bigger than or equal to n naught. Okay. So this is invertible, and A inverse an inverse whole inverse is given by summation n equal to 0 to infinity 1 minus A inverse an whole power k n, and norm of A inverse an inverse, this is less than or equal to 1 by so this is less than or equal to summation n equal to 0 to infinity norm of 1 minus A inverse an power n. So here we can say that this is less than or equal to, we know that 1 minus look at this term, this is less than 1 by 2, so this whole thing is less than or equal to 1 by 2 power n. So this is nothing but 1 by 1 minus 1 by 2, that is 2. So this term, so we have concluded that norm of an inverse A is less than or equal to 2, and this is true for every n bigger than or equal to n naught, because from the beginning we are saying that by inequality 1 norm A minus an less than 1 by 2 times norm A inverse after nth stage. So the same thing we are carrying on. Okay, so our idea is that we want to show that norm an inverse is bounded by some constant. So we have norm an, so we have so we want to look at norm an inverse, then write this as norm of an inverse A multiplied by A inverse, but we know that this is less than or equal to 2 times norm A inverse for all n bigger than or equal to n naught. So we can say that after some stage this norm an inverse is bounded by some constant. So on the whole we can say that therefore norm an inverse norm A inverse, this is less than or equal to 2 times norm A inverse square multiplied by an minus A for all n bigger than or equal to n naught. Okay, so this is enough to conclude that this goes to 0 as n going to infinity, because an converges to A. So from this we can say that an inverse converges to A inverse, so we can say that the map A going to A inverse is, therefore the map A going to A inverse is continuous on G of A. Okay, so these are the two important results we have proved, that whenever norm A is strictly less than 1, then 1 minus A is invertible, and 1 minus A inverse is given by the Neumann series, and the set GA is an open set, and the map A going to A inverse is continuous on GA. So we'll stop here. In the next class, we'll discuss about some more important properties. For example, we discuss the spectrum of an element in a Banach algebra. I'll stop here. Thank you very much.